Swayam Prabha. Digital India. Educated India.
Welcome back. Yesterday we were in the previous session we were talking about this thing, that is all x mx. We know the structure of M with respect to the model M and G, that is all the three individuals A and B and C do belong to the denotation of M, and we checked that for G, because all three value assignments G prime 1, which is basically G, and G prime 2 and G prime 3, all of them makes this mx. For with respect to all of them, this was 1. That is why we decided that this also must be 1. But now the problem is, now remember that this is what G does to it. This is what one specific G does to it. What is this one specific G? We started our journey here. This is our step 1. Then we varied x in a certain direction. After C, x took B, and then it took A. Now this is one path. This is one path which travels like this. A1 to 2 to 3 and stuff like that, but not that G is every path. Now how do we understand this? Let us try to understand it this way. Suppose somebody wants me to calculate 4 times 5 times 6. What do we say? Now what is the product of 4 and 5 and 6? This is the question. Now you see there are different routes we follow while calculating this. We may follow, for example, we may start with this. We may start with 4, then multiply 4 by 5, and then multiply 5 by 6. We get 120. But this is just one way of doing it. We could have done it this way, that is we could have started with 5 multiplied by 6 multiplied by 4, that would once again give 120. So the point is, the product of 4, 5, 6 should not depend on any order, but our calculation has got an order. We finally have to say that our calculation, our computation did not depend on any order, that is whichever order you may have, it will be the same result. Here also it is the same thing. There are two different things. One, the value of it, just by checking one order you know the value of it. You do not have to check all other orders, because you know that multiplication is commutative, which means that whichever way you multiply x and y, you get the same result, or by extension x, y and z, you get the same result, because we know that the order actually does not matter. But we started with an order. What was it? Our order was 1, then 2, then 3. If there are 3 numbers we multiplied, it was 1, 2, 3 in a sense. So the result we have got is to some extent for product 5, product 6 with respect to the order 1, 2, 3, which is a specific order, but the calculation does not, we need not recalculate it for doing it with respect to each and every order. At the same time, we have to ensure that all orders are covered by covering one order, right. That is, if we did it this way for 5, 6, if we did it this way, then also we would get the same result. So just to say that, so by one checking we talk about all these different roots, 6, 5, 4, even this. So the order here is 3, 2 and 1. So whichever way you take. So in a sense we must remember that not only are we communicating with human systems, but also we are communicating with intelligent machines. They don't know this, so we have to tell them that we are done with our checking. Now the G doesn't matter, because one G, checking one G, that is checking one path, checking one direction, is checking all directions. So which is something like for all G. So we have considered one G, but for all G it must be the same thing, like here, like 1 2 3 gives you 120, 2 3 1 gives you 120, 3 2 1 gives you 120, whichever, or 3 1 2 gives you 120, whichever direction you take you get one result, 120. So for that, just for saying this, there is another rule, that is this: for any formula phi of L1, the reference or the notation of phi with respect to m is 1 if phi, that is the reference of phi with respect to mg, is 1 for all value assignments g. Now if one value assignment g computes it, all value assignments G also have computed it, as we have seen here. So but we need a rule to say that the moment we calculate something with respect to G, that is with respect to one direction, we also calculate that very thing for all other directions. We do not have to recalculate for each and every path, for each and every direction. So for saying that, just to get rid of G, we have another rule. So the moment we know this, we can easily say that once we have got this, we can just say therefore by following this rule. So the first rule, the first thing is because, so you see this is 1 if and only if this is 1, if and only if this is 1. We have seen for some value assignment, for all value assignments G, and we have seen that is this rule, that phi is a formula and u is a variable, whatever, this is the construction. All u phi, that is our all x mx, is 1 if and only for every value assignment G prime, such that G prime is exactly like G except possibly for the individual assigned to u by G prime. The denotation of phi with respect to m and G, 1. So that is what we have seen, we have calculated for each and every value assignment, this, this and this, phi which is our mx is 1. Therefore we say that all x mx is 1 with respect to m and G. M is the model and G is the value assignment function G. Now the next step is, so we say that by following rule here, what guides us is the rule 8. So we just write, we can write rule 8, B8. But now we haven't got rid of the G, as I said. It is still specific to one direction, that is 1 2 3, where the first one was x takes c, then the second one x takes b, and the third was x takes a. But this need not be the only order, we could have done it in another order. It could be x takes b first, then x takes c, and then x takes a. It could be anything, but just by doing this, but since we have since we know that just by checking one direction we have checked all directions, like this case, now we can say therefore for all x mx with respect to m is 1. So the rule here will be actually this is section C, if this is section C, then it will be C 1. So this is how we understand, just we calculate one kind of thing, but that's not all. Then we also need to check, for example, rule 9. We haven't done this. So just I need to make some space for doing it. Now for us it is this formula. What is the denotation of Ex, that is sum x mx with respect to m? Other things remain the same, so the structure of m we already know, and everything. And how do we know it? We know it here. This is the model. This tells us that this is the structure of m. We just get back to the old page. Okay, fine. Now what is the rule here? Now this, that is sum x mx, has been derived from mx. What is the rule? The rule they have followed here is B9. So following B9, that's the syntactic rule. So following that, there must be some semantic rule corresponding to it. So here that B9, but that is syntax, and correspondingly we have semantics B9, and that rule is this one. So which is, if phi is a formula and u is a variable, so phi is our mx. If u is a variable, u is our x, then the denotation of sum u phi with respect to mg is 1, if and only if for some value assignment g prime such that blah blah blah, you know what is it. The most important point is this, that is phi with respect to mg is 1. So we have to look for at least one value of x for which mx is true. Now we find it even g, because all a, b, c, all three belongs to it. We can see that from just from g prime 1, which is g itself, that mx with respect to m and g, what this is just g, because g only assigns c to x, is the denotation of m with respect to m g, and then it is actually c, and we know that this is 1 because m is actually the denotation of m is the set that consists of all three. So therefore this is 1. Since this is 1, we can say that. So we need not check other value assignments. Once again, here the checking is very easy, because by checking 1 we have checked all. So we are satisfied because the first case satisfied us. We need not go to the second and third and the fourth case, but just by satisfying the first case, we have satisfied all other cases. So that way it is pretty much like the old function, the previous function, that was all x sum x. Here it is different, because in that case you had to actually physically check all others, and here you are doing the physical checking by not doing the physical checking. Just by doing the physical checking of 1, you are doing all. So then the next step, so this you write, then you just write therefore sum x mx with respect to mg is 1, and the next step will be therefore, so this is rule 9, just write B9, of course semantics, and then because this is the thing, you say that therefore sum x mx with respect to m, so g is gone, is 1. So this is how we calculate the value of 1 plus predicate in this system, but it becomes complicated when we have 2 plus predicates, because it is evidently way more difficult to do that. We shall see what we can do when we have something as complicated as, for example, let me do it. Okay, so I can this is the model. So how we can see how G varies. Look here, this is, so these are different G primes. Now look at this G prime, this G prime gives, this G prime gives A to X and then A to Y. So this is a layered G prime which assigns values to both. So that means that in this we are considering two variables X and Y. So two active variables are working together. We need to have such cases. So this is a case we require. For in the previous one we just needed G something and X or G something and Y, but in this case it is different. So when we have 2 plus predicates, we need to have a combination of this. So because there are 2 active variables, now we need to understand what we can be doing by using this. Now let us solve some examples so that we can understand what goes on here. Determine the value of this thing. We know the value of L. So the value of L, I just want to write down, you find it on this page. Yes, so this is the value of L. So we need this value. So we go back to the old one. Well, so L, the value of L with respect to M and G is AC comma BA comma and CA comma and CC. So if we interpret, we try to interpret L as likes, then it means that A likes C, B likes A, C likes A and C likes C, and nobody likes anybody else in this system or in this model. That is what it is trying to say. Now how to determine the value of, how to calculate or compute the value of this thing. You see, this is, there are 2 steps in it. So the basic formula is LXY, which is formed by using B2 of our syntactic rule, B2 of syntax, where this is a term and this is a term and this is a 2 plus predicate. So they combine, they get combined and they make LXY. And then we have, because this is a formula, now we are adding all Y to it. So then it is the next step, all Y. So now this thing is the next layer of rule, and this is our B8 of syntax. And then this is a formula. So now we are adding some X to it, and here we are having rule B9 of syntax, and this is how the whole thing is constituted. And this is a perfect formula because each step is the formula that we know. Now we go to the semantics part of it. So each step, at each step we must have some semantic rule, because we have seen that the whole point is the moment we have a syntactic rule, it must have a semantic counterpart. So we shall see how it works. Now we just, for the time being, block this part and consider this part. So because we are calculating the value of it, or we are computing the value in steps. So the meaning of, or the denotation of all Y LXY with respect to MG is 1 if and only if the denotation of LXY with respect to M, we want to have G here, is 1 for every value assignment G prime, such that G prime is exactly like G except possibly the individual value assigned to Y by G prime. And so that is about Y. So what about X? Since X is not relevant here, X is not active, because we are talking in terms of Y here. So we are at this stage, we are at step 1. So, for us the active variable is y and not x. Then what will x do? X will, we know the structure of G, which is all the time important. So, G is x gets C, y gets B, and Z gets A. This is the structure. This is something we need to understand, we need to remember all the time. Now, then we can see that x gets C, that is G assigns the initial value assignment function, G assigns C to x, we know that. So, what we need to check? So, if you have something like L x y, x will collect, because x is not an active variable here, x will collect its value from C, but y is an active variable here. So, y will vary. So, G assigns B to y, but then G primes, we need to check G primes. What is the checking type? All x. That means for all value assignments that assigns values to y, we must find that C somehow is connected to that value. That means y is varying. That means we need to find that all C A, all value assignments, right, must belong to L. Similarly, C B, C is fixed, but B is varying, must belong to L, and also C C must belong to L. This is what we have. If this has to be 1, then this must be the case. Now, what does it mean? It means that C, that means y will vary. So, y will have A, B, C, and C has to have this coupling with y, with the varying y. That means that all these three things must be members of the set, which is the denotation of L. Is that the case? We find C A. Yes, we do. We don't find C B. We find C C. Two things are there, but unfortunately, this is not there. Hence, so in a sense, we are saying that when we have a case here like this, you have to satisfy the AND case, right? That is, you must satisfy, you must have the pairing like C A and C B and C C. So, like it's a case of AND, right? So, hence, since the AND preposition, like a preposition having AND, is not true, we must say that the value of this is I have typed all these things, whatever I said here, that since C C does not belong to L, we must say that this part is 0. Now, now we need to check whether there is at least one value assignment G prime such that E A belongs to L and E B belongs to L and E C belongs to L when G prime assigns E to X in this. We need to understand this. We have just said this. What is our next step? Our next step is then what is the value of sum x all y L x y with respect to M and G. We have done this much somehow, but now we have arrived at a stage where both the variables are varying, because this is derived from L x y, where x takes sum x and y takes all y, right. That is, I wanted to say that x is bound by sum x and y is bound by all y. What does it mean? It means that both will vary, but they will vary in different ways. Here the requirement is at least one value of x must somehow satisfy something, right. But there the requirement is all values must satisfy. That means, but we start with sum. So, for some x, so we just check that for some x, is it the case that all y's are satisfied? That is, for some x, is it true that L x y is true for all the values of y, right. So, how to say this? We say it formally this way. We just say that if we want to write it, we can write like this. Sum x all y with respect to L x y, sorry, sum x all y L x y with respect to m g is 1 if and only if there is some g prime, that is value assignment g prime for which L x y with respect to m is 1 for every g prime. So, the first thing, you see, the starting point is some g prime, some g prime that assigns value to we are not writing some g prime that assigns value to just to x, and then we are looking for another g prime that assigns values for y. So, so we need to add those things. So, how could we add? Here we could have written some g prime as we have seen in rule 9 such that g prime is exactly like g, except possibly for the individual assigned to, now in our case it is the first individual is x with sum to x, and for this g prime we add g prime such that blah 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 exactly like g except possibly for the individual assigned to y, right. So, these are the qualifications. The first one gets this and the second one gets this. Now, what does that mean? That means that our checking now has come here. We have to check two different things, but the starting point is definitely x not y. So, we have to search for, we have to look for some x. I will try to give you a picture of this thing, so that we all can understand what is going on, but I need to make some space for this. So, there are three options for x. Our starting point is x. What we are doing is this: we need to check whether A is something for which, now this is a case of AND, all the three things, right, that is A and B and C are paired, or rather the three combinations, all the three combinations are there in the structure of L, which we know already now, or B is something where this pairing goes, or C is something for which this, what I mean by pairing is this pairing. That means if we find just one thing, if we find A such that A belongs to L, A B belongs to L, and A C belongs to L, we are happy. But you see, in this case, because it is all, it has to be all three, and in this case, because it is sum, in the case of, in this case, because it is sum, it will be or. If we find A or B or C to satisfy this, then we are happy. Now we notice that we see all the values. Now one value we have already checked. What is the value? On the previous page we have seen that already this pairing. So for the pairing, the C pairing we have checked, right. So this one we have checked, and we have seen that it is not satisfied. Now this is something we need to understand, that the first step we did, that is this much, is this checking, but still we have to check. Had it been all, then it would be enough for us, because we can see that at least one thing does not satisfy. But then because it is not all, because it is sum, we need to check more. We need to find, is there anything that satisfies. So that is, if there any value of x that which pairs with all other values like this, if it is A, then like this, or in general we can say it is E. So we are trying to find some value E such that all EA, EB and EC do belong to L. They all belong to L. Do we find any such thing? Now if we get back to the structure of L, unfortunately no, because C is there, but A and AB are not there. B, now BA is there, but where is BC? BC and BB are not found. AC is found, but then AB and AC are not found here, and CA is found, CC is also found, but CB is not found, right. So they are not there on the list. That is the reason there is none that satisfies our condition. Therefore the value of this, the value of the whole thing, will be 0. So what do we write? We write that it would be, we have said already, we said that we have written the condition for this, and now we say that since there is no value assignment G prime such that G prime is exactly like blah 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 with respect to x, for which L x y with respect to M is 1 for every value assignment G prime such that it is exactly like G, except possibly for the variable, in this case the variable is y, right. So you just you have the language from the rule. I am not writing the whole thing, but this will be the structure. So since this, therefore we say that the value of this will be 0, right. So this is how we calculate one one thing. Now we may consider the next thing. Then here the basic formula is L y x, and the checking direction is from y to x, because we start with y, and y is bound by an all. Y is bound by an all y, and x is bound by some x. X is bound by some x. Now we will see, as we have seen, the checking goes from y. So, and this is an all case. All means and, as we have seen previously. So what we have to check is this. We have to check whether here we have A and B and C, and here we have A or B or C. We have A or B or C. Once again we have A or B or C. So what is it we need to check? We need to check whether there is any combination of A and A, or A or B or A or C, whether any such thing, any such pair whose first member is A is part of L, and we have to check whether any pair whose first member is B is part of L, and similarly any pair whose first member is C is part of L. Now what is the checking? This should be an AND. That means we have to check it for all three, A, B and C. The first member is A, so we need to find all three. So so yes, we find AC. So AC is there. So one part is satisfied. So then the entire part is satisfied. All the A part is satisfied. Then B, we have BA. So BA is there. So once again the entire part is satisfied. And then we have CA. Also we have CC, but anyway one will do. So CA. So the entire thing is satisfied. So the AND is satisfied because all three are satisfied. So that's why the answer will be this is 1. So actually there are steps MG1, and then G will disappear, and we just get the entire thing to be 1. That's the last step. So just do it, and very easily we can determine, we can decide. But then the question is, if we have to vary both, if we finally have to check the truth value of the whole thing anyway, what is the point in having this in parts? Have you seen that we started with some y L y x? What is the point in doing it? The point is this. You see, we are doing it in parts. Even while checking it, we checked 3 parts because we have to do it, because there are 3 individuals. So our checking must have all these 3 roots. This is to tell that, or this is to somehow show that when you do this much, when you calculate just like part of it, you are done with some part of your final calculation. For example, in the case of this, where you have sum x L y x, what is the value of it? We need to understand. Now the value, you see here y is varying, x is varying, y is not. So where will y take its value from? From G, and we know that G gives y B. Let me confirm. Yes. So this will be B. So the point is, is there any value, and this is sum, if there is one value of x for which, like one value e of x for which B is a member of L, then this will be 1, right, if and only if. Do we find such thing? Yes, you see BA is already a member. So if E is A, then it is fine. So BA is a member of L, therefore this will be 1. But now you see here also we did that part. So just by doing this part, you have, so the point is, one bit of the big calculation is already done by the small calculation. So it is a sub route of the main route you have travelled, just to show that already you have travelled some route by doing the sub calculation, that is this, you actually have to do it in steps. Not that the whole, once again we need to understand one thing, that we are not communicating just with the human mind, also we are communicating with the machine mind, and for the machine mind it is very important. I have to tell the machine that the calculation has got steps, and it is not unjustified to have the steps. So actually by calculating this, we have calculated part of it in every case. So that is the reason we do it in steps. So in each and every case, and another very important thing is, you see, had this problem been something like, instead of having this, if we just had, for example, if we just had sum x sum y Lyx, then what is the value of that? Then just by doing this, just by checking this value, you actually checked, you have calculated the value of the entire thing. How? Because in that case this would be OR, that is one case would satisfy the entire thing. I am trying to tell you the advantages of doing it in steps. You do not have to do the entire calculation, because what is the requirement? The requirement is at least one should have at least one as a pair, right, at least one value of. So if it is EF, the general pair is EF, then at least one value of E, one value of F must be such that EF belongs to L. And because it is just at least one value of E, if B satisfied this, B does satisfy, because BA is part of this, you have actually checked the truth value of this, right, just by checking one part of it, because automatically Y gets B, and then you know that BA is part of it. So if E is B and Y A, then EB actually belongs to L, or to the denotation of L. So just by checking here, in this case at least one part, you have checked the entire thing. That is the reason, not that when it comes to all you have to check all cases, but when it comes to sum, when had this been sum, it would be very easy for us. So yeah, so there are all these things when it comes to this calculation, and with that we are in a position now to start talking about the English-like system L1E. In this session we will just see the syntactic rules, and in the next two sessions we will talk about the entire thing in details. So L1E is once again a first order predicates English-like language. Why English-like? Because here you do not find all A, B, C, X, Y, Z, you find real words like Hank, Les, Sadie and all that, and sleeps and snows and loves and hates. all that. So this is our vocabulary. It's a very small one. We have 3 names, Hank, Liz, and Sadie. These belong to the category N, and then we have 3 variables, V1, V2, V3. We could have more, but ideally we should have through Vn, but 3 will do. And then we have the category Vi, and there are 3 members to it: sleeps, snores, and is boring. And we have constants, so loves, hates, is taller than. Sorry, these are constants of category Vt, that is, these are 2 plus predicates. And then we have another additional constant here, or another additional category. What is it? The common nouns. So we have man, woman, and fish, just that, nothing else. So the syntactic rules. And of course, we have the logical constants as usual. And we could also add if then, if we want. We can just add this. Now the rules. If alpha is a Vt and beta and n, then alpha beta is a Vi. Now n, you remember that n may either be a name or a variable, anything. So by having this rule, we can have something like so our 1 plus predicates are man. Our 1 plus predicates are sleeps, snores, and is boring. So not common noun, 1 plus predicate. So we can have something like Sadie snores, or we can have V1 snores, or we can have something like V3 is boring. We can have all these constructions. You see alpha beta, so this is alpha and this is beta. So this is the first rule. What is the second rule? The second rule is if alpha is a Vt and beta and n, then beta alpha is a formula. So so now we need the, so first we converted a Vt into a Vi, and then I think I need to revisit what I said. So this rule will rather be this. I'm sorry for this mistake. This rule is if beta is an n, that is a name variable here, and alpha is a Vt, that is it is Vt. We have how many Vts? We have loves, hates, is taller than. So we take loves, for example. If you have loves and you have a name, so you can have anything. You can have V1, or you can have Sadie. So Sadie loves is a, by combining this, you get a alpha is a Vt and this, then alpha beta is a Vi. So all these things are Vi's. Loves V1 or loves Sadie, these are Vi's. And then this is rule 1. What is rule 2? Then if alpha is a Vt and beta is an n, then beta alpha is a formula. So what does it mean? Once again, alpha and beta. If alpha is a Vt, so it is a Vt, and beta is an n, then what is a Vt? We can have there is a mistake I can see here. So actually this is not Vt, this is rather Vi. So I just correct it here. So this is Vi. So anyways, now if alpha is a Vi, and beta is an n, and Vi, if this is the case, then beta alpha is a formula. Now this is This is another thing. Now, VIs are of two types. Either you have a formation like this, that is loves Sadie, that is one kind of VI. Also you have loves V1 or hates V2. These are all different VIs. That is one VI which is constructed, and also you have a natural VI like sleeps or snows. So we just write that also. So snows also will be one VI or sleeps. So and N we take Hank, anything we can take. Now everything now is kind of a formula. So Hank loves Sadie is a formula, Hank loves VI is a formula, Hank hates V2 is a formula, Hank snows is a formula, Hank sleeps is a formula. All these things are formulas. And then if alpha is a neg and phi is a formula, then alpha phi is a formula. Definitely if this is a formula, then it is not the case that neg means it is not the case that it is not the case that Hank loves Sadie must be a formula. Here you see that neg is, it is not the case that. So it will be basically it is not the case that blah 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 Hank loves Sadie, which is a formula. Now for conjunctions it's the same. For conj there are conjues of three types here, and or if then we add it, but yes it would be the same thing. If you find two formulas, then you can combine them through any logical constant and or if then. Now very important rules here which we didn't have before. One is this: if alpha is a CN, that is a common noun, there are three common nouns, man, woman and fish. U is a variable, then phi is a formula containing at least one occurrence of U, then phi prime is the formula where phi prime comes from phi by replacing the leftmost occurrence of U by every alpha, and alpha, remember alpha is a common noun, and each subsequent occurrence of U by that alpha. What does that mean? It means that suppose phi is V1 loves V2. Now there is so what is our U? Our U here is say V1, and that means we are working on V1 here, and so there is just one, then there is one we are considering just one variable here. And if there is a common noun alpha, now alpha, suppose alpha here in this case is man, then by this rule, that is B5, what we get is, so you just add sort of, you add here, you just add man and V1, that is with respect to V1. This means this is the notation we are going to use for convenience by following B5. What we get is then phi prime, which is nothing but, so V1, this is the leftmost occurrence of the sorry, this is the first occurrence of V1, the leftmost occurrence, there is no other occurrence, so it's just one, it does not matter. So then we are considering just the first occurrence of V1, we get some man loves V2, that is F prime, sorry phi prime. So phi prime is derived from phi. Now what about, what if we get xi, for example, and xi is suppose this, then V1 loves V1, suppose it is like that, and then we add once again man, same thing, man to it, and V1, that is with respect to V1. Now, you see the first occurrence, that is this one, will be replaced by some man, because we are using the same rule B5. Then subsequent occurrences, this is the leftmost, that is the first one, which is to be replaced by man. Then the subsequent occurrences must be replaced by that man, that, and then that common noun alpha, man is our alpha. So, from this we derive xi prime, which is the first replacement will give you some man loves V1, and then the second replacement, the subsequent occurrences of V1, you are supposed to get that man. So, some man loves that man, to say that they are the same person. Now, this is a limitation of this language. Unfortunately, it cannot have something like himself or herself. That is a problem of this language, but what to do, it is like that, we have to manage. Now, suppose this is our phi, and now here we are going to talk about B6, then what will happen? Everything else remains the same. Now, by following B6, you see alpha is a Cn common noun, and alpha here is man, and u a variable. What is our u? This V1, and phi is a formula containing at least one occurrence of u, that is phi. It has two, it has exactly one occurrence of V1, which is our u. Then where phi prime comes from phi, yes, by replacing the leftmost occurrence, which is this of u by some alpha, that is some man, which we have done, and each subsequent occurrence of u by that alpha. We do not have any subsequent occurrence here. So, here this derivation is fine, but here well, actually I was doing B6 first. We have done this for B6. Now, we consider B5 where we have every, right. So, every is, so the rule seems that the rules are exactly the same except for the quantifier. So, this is the every rule, and this is the sum rule. This is a sum rule. So, we did the sum rule first, not a big deal, and we are right in writing B6 here. Now, let us consider B5 is the same thing. Yes, so it is 5 and 5, it is phi, and phi is B1 loves V1 loves V2 and all that stuff. What you get here, not by using B5, you get not some, but you get every man. That is the only difference. You get every here. Every man loves V2. So, we will go to the next session now, and we will talk about this.